this video, I want to talk about the conservation of energy, or the principle of the conservation of energy, and how we can use it as a tool for solving dynamic problems and kind of what it does for us as a tool. So the conservation of energy in the most basic sense is the idea that energy cannot be created nor destroyed, but it can change state. It can change form, and we can change how it's stored or how it's released. So if I wanted to kind of give maybe a simple example to that, let's take an example of a slingshot. And the slingshot, if that looks like a slingshot, is holding a stone. And when the slingshot is drawn back, we are storing energy in an elastic form. So energy is stored in the deformation, the stretch of the rubber portion of the slingshot, the elastic portion. And if we knew more about that, the properties of that material and how much it was being pulled back, we could calculate how much energy is being stored there. But barring that information, what we know is that as soon as we release that elastic energy, so we let go of the stone, it gets propelled forward and it gets converted. Let's give myself a little more room. It gets converted to kinetic energy due to the velocity of the stone as it's traveling. So immediately after the stone has left the slingshot, it now has velocity, and that velocity is, for our purposes, recorded as a kinetic energy. So as this stone travels, and it travels up in the air, eventually coming back down to the ground, where it strikes the ground with some force. And as it travels through this path, which we've seen before, this projectile motion, parabolic curve, it's converting kinetic energy into potential energy. So it travels up here. At this high point, it has some peak in potential energy. So its potential energy is up, its kinetic energy is down. Now, one thing that we should note here, compared to when we've looked at projectile motion before, the kinetic energy is not necessarily zero, right? Because the stone still has horizontal direction velocity, so it still has kinetic energy. But at the peak of this parabola, its vertical direction velocity has gone to zero, and it's instead been converted to potential energy. So we've got some new potential energy up here. Now, as the stone then travels down, it makes some sort of impact with the ground on this side, where the potential energy is now down, and the kinetic energy, due to the work done on the stone by gravity, the energy added into the system by the force of gravity, has caused potential energy to come back up, and the stone has a higher velocity as a result. So I mentioned something in there that we want to think about, which is work. And work can sometimes be used almost synonymously with potential energy, or the change in potential energy in a system. The act of doing work is the change in potential energy. So work and energy both have units of joules, and in a simple form, the conservation of energy equation could be viewed in this way. And I'll explain this equation in just a second. So recall before that we used the letter T to denote kinetic energy and the letter U to denote potential energy. So the way I'm using this equation is that we have a kinetic energy, T1, at state 1, or maybe time 1, however you want to think about it. And we do work on the system, on the object, whatever it is we're isolating, and we cause a change in energy from state 1 to state 2. So this could be the force of gravity acting. It could be the addition of some force that we put on the stone, maybe through a slingshot, for example, or any other kind of input to the system. And the result of the addition of those two forms of energy is a kinetic energy at position 2, so labeled T2. And this is just a simple form of doing or examining the conservation of energy, and it neglects several possible sources of energy, but for our purposes, it's a good place to start. Now, the other thing I wanted to mention about work is that we often obtain a change in energy due to a force being applied to something. So work can be sometimes written as force times displacement, or the energy due to a force being applied over a distance. Remember that joules can be broken down into Newton meters, and this kind of shows that most directly. Force representing newtons, displacement being represented by meters. So Newton meters most directly is equivalent then to work, or the units of joules. So for example, if you imagine a staircase and there's a person, let's see if I can draw, probably not, a good stick figure person here walking up the stairs. And as that person is traveling up the stairs, their legs are applying a force to their body, projecting them or propelling them up the stairs. As they travel up the stairs, their potential energy is changing, right? There's a displacement of their body upwards in the vertical direction. And we could calculate the energy expended to do that if we knew how much force they're applying and how much displacement they are undergoing. So these two things would allow us to calculate the work being input to the system in that case. All right, so we'll explore this further as we look at some example problems in the next videos. Thank you.